Oh, hi. I'm Andrew.
I'm Neil. Any questions?
Hi, I'm Stephany.
Stephen Turner.
Hi, I'm Peter Wysocki. Hi, it's Peter again. So what I'm going to talk about is how to find these exoplanets. So in order to find the exoplanets, one popular method we use is the radial velocity method. In this method, we detect exoplanets by looking for the wobble the exoplanet induces in the parent star. So how this works is that in a system, the bodies will orbit around the center of mass. And so if we have a two-body system of a star and a planet, the center of mass will be slightly off-center from the sun's mass because it's much, much, much more than the planet. So if the center of mass is around here, let's say, then when they orbit, you can see that the sun will just appear to wobble and not really go in a big circle like the planet does. Whee! So that is what the wobbling is from. But
I'm here to talk about one of the methods used to spot exoplanets. This method is called the transit method. Basically what happens is we can measure the brightness of a star, and when a planet passes in front of that star, the brightness dims, and we can measure that dip in brightness, and then we know that there's a planet or something else passing in front of that star. I'm going to demonstrate here with this flashlight being my star and this tennis ball being a planet. So this is the brightness that we measure, and as the tennis ball passes in front of the flashlight, you can see the dip in brightness. That dip is the planet passing in front of the star. There is one major flaw with the transit method though, which is that it requires the planet to pass between the observer and the star. I'm going to demonstrate what that means here. So, this is the star that we are observing, and this is us observing from Earth. So, when we look, we see this planet here passing in front of the star, and so we are able to detect the planet. We can see the dip in brightness when it passes in front. However, if the planet has an orbit such as this, when we look for it, it won't pass in front of the star. And so a large number of planets go undetected because their orbits don't pass between the observer and the sun. This also means that orbits that are close to their star, planets that are orbiting close to their star, are more likely to be detected because you can have more variation in the orbit when it's close to its star. And what I mean by that is if you take the same orbit and extend it further out, the planet is now here, and when we observe it, it is no longer in front of the star, and so we cannot see it. And therefore, there are a large number of planets that we cannot see, and most planets that we can see are very close to their star.
Hi, today we'll be talking about the Goldilocks zone. In exoplanets, the Goldilocks zone is quite important. The name comes from the fable Goldilocks and the Three Bears. If you remember, Goldilocks was a girl that went into a home and tried 3 types of porridge. So today we will be explaining how this can help us understand the Goldilocks zone in a planetary system or when looking for an exoplanet. So let's imagine this flashlight is the sun. set it here, close to these three bowls, which each represent a planet. This one's closer, this one's in the middle, this one's a little farther away. We're going to try each one, just like in the Goldilocks fable, and see what happens. That's really hot, and it's quite close to the sun. So you can imagine in a planetary system like ours, that could be Venus or Mercury. Now we're going to try one that's farther away from the sun. Ooh, that's cold. It's a little farther away from the sun. But here, in this middle one, it's just right. Not too cold or not too hot. Why is that important? Well, water is really important to sustain life. And when we're looking for exoplanets, we want them to lie in the Goldilocks zone. So this area here would be the Goldilocks zone. This one was too hot, so water would evaporate off the surface. This one was too cold. So like Jupiter or Saturn, water freezes or there's just it's just too cold to sustain life. On Earth and Earth-like planets, water can stay on the surface, and it's essential to sustaining life. That is the Goldilocks zone.
How do you plan a space party? You plan it. That's right. Planets are what we're looking at next. First on our list are the wonderful hot Jupiters. Like Stephany mentioned in the Goldilocks zone, some planets are going to be way too close to the sun for comfort. Those planets, when they're as large as our own solar system's Jupiters, are called hot Jupiters. These planets will be very, very close to the sun, which is what makes them easier to detect using the transit or wobble methods. Also, some of these planets orbit so close, their atmosphere actually burns away, leaving only an inner metallic core behind. But who wants to live there? We're all looking for a planet a lot like ours. That's what brings us to Earth-like planets and super-Earths. Earth-like planets are ones that resemble and are very close to the size of our own Earth. Super-Earths don't have any superpowers. We're actually much, much larger in size. However, we have a bit of a problem with those planets. On Earth, you might weigh what you typically do, but super-Earths that are 2 to 3 or even 4 times the size of Earth, you're going to find you weigh a lot more. But life doesn't only have to be found on planets. Some can actually be found on moons. Moons of much larger planets, like gas giants, are large enough to actually hold life. However, sometimes they're too far away from the sun to get enough light to heat it in that way. But due to tidal forces, they can actually generate some heat. Tidal forces are what happens when the gravity of a very large planet is pulling and tugging on a much smaller moon, even if it's the size of Earth. As the planet turns, the force of the gravity squeezes and pulls it, which causes it to generate heat on the inside. That heat can warm up the temperature to make liquid water, which is important to life. One moon like that is Europa, which is currently orbiting Jupiter.
Scientists have been interested in sending messages to planets beyond our solar system for many years now. In 1974, the Arecibo message was sent to the globular cluster M13. This cluster contains about 300,000 stars and is over 22,000 light years away. Based on current estimates, it'll take over 25,000 years for this message to reach M13, which contains the numbers 0 to 10, the human DNA sequence, the depiction of a human, and our vision of the solar system. If any extraterrestrial civilization managed to receive this message and sent out a reply, it would take yet another 25,000 years to reach us. More recently, the Rubisca message was sent out in 2009 to nearby stars, the Tea Gardens and Capaceti. And this message contains genetic code for the Rubisca protein, which terrestrial planets use for photosynthesis. In addition, the Lone Signal Project, which was just started a couple years ago, aims to send out 144 character messages to the nearby star Gliese 526. This star is about 17 light years away, but this project actually lays the groundwork for future projects to send interstellar messages to planets beyond our solar system.